We tend to classify minerals based on their chemical makeup, based on the pieces on a microscopic level that make up those minerals. One of the classes that we talk about a lot of times are the silicates because they have that SiO4 4- tetrahedron. But there are a ton of other different materials that can go into a mineral, and we tend to classify them based on the anion in the material. So silicates have the SiO4 4- tetrahedron. It's an anion because it's got negative charge. But then there can also be chlorides that have Cl-, sulfates that has SO4 2-, oxides that have O2-, sulfides with S2-, and there can even be native elements that don't have any ions at all. So we're going to look at each of those classes in this identification segment. Oxides are one other class of mineral aside from the silicates. We've got a few different oxides that we can look at. Hematite and magnetite are both important oxides in rocks at Earth's surface. Both hematite and magnetite have this O2- piece in them. That's the anion in oxides, and so that's what makes them oxides. Hematite and magnetite also both have iron in them. So in hematite, it's 2 irons for every 3 oxygens, and in magnetite, there's 3 irons for every 4 oxygens. Very similar structures, and also, just looking at these, they're very similar looking. In this camera view, they both look kind of darkish, but if we pick them up and I show them to you, you'll see that they have this sparkly luster to them. They look sort of metallic, but sort of not. So we'll tend to call these submetallic. Their luster is submetallic. It's not non-metallic, it's not vitreous, it's submetallic. It's sort of semi-metal-like. Both can be black or silver, so it's tough to tell them apart there, and both can be hard enough to scratch glass in some cases. The difference comes in a few other properties. So the property called streak can help distinguish them. Streak is when you take one of these porcelain plates and you scratch a mineral against it, powdering that mineral. So here I'm going to test the streak of hematite. You can see it leaves behind a powder, and that powder has a characteristic color. Even when the colors of a mineral change, the streak tends to be much more constant. So that's the streak of hematite. Now I'll take magnetite, do the same thing. That's the streak on magnetite. There is a subtle difference there, but at the top, you see the hematite streak has a reddish color to it, and the magnetite streak is much more black. So that's one way that we can distinguish hematite from magnetite. Hematite's always going to have that reddish streak, and magnetite's going to be more like a black streak. Hematite at times can be soft, so some samples aren't hard enough to scratch glass. And also hematite can be red. It's actually a major component of rust. So hematite, we see it all the time. It also stains sandstones and other minerals red, but it is a major component of rust at Earth's surface. The main thing about magnetite, as you might expect from the name of it, is that it is strongly magnetic. This magnet sticks very strongly to this, does not stick to the hematite. Sometimes you'll see that they say that hematite is weakly magnetic. That tends to just be tiny little bits of magnetite mixed in with the hematite. So really, magnetite is the magnetic one, hematite is not. Here are the structures of hematite on the left and magnetite on the right. You can see they're pretty complicated looking, and you don't see any silicate tetrahedra in here because there's no silicon in hematite or magnetite. These are oxides, and so the negative charge is carried all by the red oxygen atoms. And then the iron cations are the positively charged particles here that are in tan or sort of yellowish brown. In hematite, they are arranged in sort of layers. When you turn and look at it from this angle, you can see that there's layers of oxygen and then layers of iron and layers of oxygen that are somewhat distorted. And then in the magnetite structure, it's really difficult to see any of those layers. Maybe you can convince yourself that you at least see, lines of those atoms going back, but it's not layered in discrete layers quite the same way as hematite is. If we switch to this polyhedral view, we don't see tetrahedra anymore, at least in the hematite structure. These are octahedra. They are 8-sided shapes, triangles all around. And so the iron sits at the center of each of those octahedra. In magnetite, it's a little different. There are a bunch of octahedra, but mixed in there, you see some iron tetrahedra as well. So the environment of iron is a little bit different in magnetite than it is in hematite, and that's what allows magnetite to stay magnetic. We're not going to talk in any more detail about that, though. You might classify this mineral, well, it's not really a mineral, it's called bauxite, in with the oxides. It's not one mineral, and you can see by looking at it that it looks like it's sort of zoned, and it has all these different spheroids of different colors. These spheroids are maybe dark gray to black in the middle, and then red on the outside, and then sort of tannish gray in between. By looking at that, you can tell it's not just one thing. It's a mixture of different things, different compositions. So it's not a mineral because it doesn't have a defined chemical composition because it's a mixture. But most of what's in there are aluminum oxides and hydroxides. So we might lump that in with the oxides if we want to. To identify the bauxite, you're really looking for those spheroids of different colors. Bauxite, we include it because it is an important ore of aluminum. That is, it is an important industrial source where we mine bauxite and we use that material to get aluminum. It tends to form because if you weather a soil for a really, really long time, all of the other metals leach out except aluminum, maybe a little bit of iron, but for the most part, you leave behind this aluminum that then if it gets reburied and lithified, then it turns into this aluminum ore that we can extract later and use for our human purposes. Sulfides are another class of minerals we'll talk about. They have the sulfur 2- or sulfide motif in them. That's where the anion is in these structures. We've got two that we'll talk about, pyrite or fool's gold and galena. So pyrite is 1 iron for every 2 sulfur, and galena is 1 lead for every 1 sulfur. Because this is lead, you really shouldn't lick this mineral especially. You'll get lead poisoning after a while. Both of them have a metallic luster. So we haven't seen a really good metallic luster yet. But if you pick this up and you look at it, it looks like a chunk of metal, the way that it shines, even when light is not directly on it. Same thing with the galena. Looks like a chunk of aluminum foil almost. That's how you know that it has a metallic luster. Both are dense. So both of these samples are very heavy for their size. Feel about twice as heavy as other rocks or other minerals like quartz. They can be cubes. You can see neither of these is a cube, but they can be cubes. Here is an example of a chunk of galena, that's the lead sulfide, that is much more cubic in shape. It's a bit broken up, but even those broken faces have these 90-degree angles to them. Other distinguishing characteristics for these minerals, you can distinguish pyrite from galena by their color. So pyrite's going to be golden color, and galena is going to be a silvery purple color. Pyrite's going to be hard enough to scratch glass, whereas galena is pretty soft. You should be able to scratch it with a copper penny. Here are the crystal structures of pyrite on the left and galena on the right. Pyrite over here is these octahedra, so 8 sides, where iron is in the middle, and now sulfur is on the corners. That's why it's iron sulfide. Galena is a very similar structure to one that you've probably seen already for halite or sodium chloride. So looking at this structure, it's just a cubic arrangement of lead and sulfur atoms stacked together. And so it makes sense that galena tends to break into cubes because its atoms are stacked in cubes. We only have one native element to look at. Native elements are unique in that they don't have ions. They consist of only one element. And so all the pieces of that element in the structure all have the same charge, 0. So sulfur is the native element that we have you looking at. Its chemical formula is simply S. Even though in the structure itself, the sulfurs are all joined to one another, as you see, we just write it as S because that's all it is, just sulfur. It's a very soft mineral, so soft that I could scratch it with my fingernail, but I don't want to get sulfur on it right now. It always has a characteristic bright yellow color and a characteristic rotten egg smell. So that's the best way to identify sulfur. Sulfur's got this really weird crystal structure, though, one of the weirdest I've seen, that's made of rings of 8 sulfur atoms, and then those rings are stacked on top of each other. sort of like Pringles, but the Pringles are stacked in different directions. So some Pringles are stacked up and down, and then some Pringles are stacked into the plane of your screen here. It's bizarre. It's strange, and you can see that there aren't really strong bonds in between those circles. There aren't actually any bonds drawn in this image between each of those sulfur rings. That's why sulfur is so soft, because of the lack of strong bonds between all these sulfur, 8-sided sulfur shapes, octagons. That's the word. Halides and sulfates are two different classes of minerals, but since we're only looking at one of each, and since their properties are somewhat similar, I'm grouping them here. Both of them are also very soluble, which is another reason to group them. So our halide mineral is called halite, and our sulfate mineral is called gypsum. So halite, is sodium chloride, so 1 sodium for each chloride. And then gypsum is 1 calcium, 1 sulfur, and 4 oxygens. And those sulfur and the oxygens are grouped together in a sulfate tetrahedron, kind of like the silicate tetrahedron. And then it's also got 2 waters in the mineral structure, 2 H2O. Both of them, as you can see, they can be clear to transparent, to translucent, to white, if in some cases, and they're both fairly soft minerals. They're both easily scratched by a piece of glass or by a nail. But halite is slightly harder. It's got a hardness 3. So no matter how hard I might try, I can't scratch it with my fingernail. Whereas gypsum with a hardness of 2, I should be able to scratch fairly easy with my fingernail. Part of that scratch there I just created. You can feel it digging in when I put my fingernail on it. So gypsum is one of our very softest minerals. Halite also forms cubes with faces that meet at 90-degree angles. Whereas gypsum you might describe as parallelograms. So you can see these faces don't quite meet at 90 degrees. There's an oblique angle to those. One really easy way, if you could lick the minerals, which I don't recommend, is that halite tastes salty. That's because halite, sodium chloride, is table salt. And if you looked at your table salt under a microscope, you'd probably see that it was made of these microscopic cubes. Here are these crystal structures of halite on the left and gypsum on the right. So halite, you can see cubes of stacked sodium and chloride ions. Again, that's why halite, sodium chloride, forms these cubes, because the atoms themselves stack into this cubic arrangement. And it's easy to break along those faces between the atoms. Here's the structure of gypsum. Looks pretty complicated. There's a bunch going on in there, but you see the calcium in blue in this image. The sulfate tetrahedra, you can see each little sulfur atom bonded to 4 oxygens there in the structure. Unlike silicate tetrahedra, the sulfate tetrahedra don't polymerize ever in any of these minerals. And they tend to break off of the structure pretty easily when you put it in water, so it dissolves pretty readily. Sulfate doesn't do quite as much as silicate, at least when we're talking about mineral structures. And then you even see some little water molecules mixed in there too, H2O, with the oxygen in the middle and little hydrogens on the side. It's not as clear looking at it this way why the structure of gypsum is what it is, but if you look at the crystal structure from the top, you do get the sense that it's likely, at least, that gypsum would form those sort of parallelogram shapes. Last but not least, the last class of minerals that we're going to look at are the carbonates. 2 carbonates we're going to look at are calcite and dolomite. Those of you doing it live, you might also have some aragonite in your box, but for the virtual lectures, we're just going to think about calcite and dolomite here. Calcite is calcium carbonate CaCO3, so 1 calcium, 1 carbon, and 3 oxygens. And that CO3 is 1 unit, a carbonate ion. And then dolomite is a mixture of calcium and magnesium with carbonate. So there's 1 calcium and 1 magnesium for every 2 carbonate ions there are. They're pretty similar minerals, even though these 2 samples look very different. They don't have to always look this way. So calcite can be clear, but it's often just white or gray, same as dolomite, or they can be stained other colors. And they're both soft. Neither of them can scratch glass. Slight difference in hardness. Calcite is a 3 and dolomite is a 3.5, but you're often hard pressed to find really nice samples like these to test against each other. The main way to tell calcite and dolomite apart from each other and apart from any other minerals is that calcite fizzes if you put acid on it. I'll show you what I mean. We'll see if we can see this on the camera. Here I have a bottle of 1 molar, so pretty concentrated, hydrochloric acid. I put a couple drops on there and you can see those bubbles instantly start to form. What's going on is the acid is transforming the carbonate, the CO3, into carbon dioxide, CO2, and that carbon dioxide is a gas, so it bubbles off very easily. So that level of fizzing tells you that this is probably calcite. Whereas dolomite, if you put acid on it, it's not going to fizz. So, put a drop there, bigger drop, nothing's happening. You can, however, get dolomite to fizz if you scratch it up, if you make a nice powder out of it. So maybe I'll take my glass plate. So you can see this is a pretty soft mineral, the way that it's creating all these scratches on dolomite. So now I've got just a little bit of powdered dolomite on that surface, put the acid on it. Don't look away. Now it does fizz, but first you've got to powder the mineral to get it to do so. One other way to tell is that calcite tends to form rhombohedra like this. These sort of, right, it's got 3 really well-formed cleavage faces, but they all meet at not 90-degree angles. So it makes what we call a rhombohedron. If you've got a nice piece like this, it's also got this other interesting property where it splits things like a prism when you look at them. It's called birefringence. So maybe a little hard to tell in this, but what's otherwise a very clear looking line, if you put a piece of calcite on it, it splits it in 2. Here's a really clear example of what would happen if you look through a well-formed piece of calcite at text below. It splits it into 2, and as you rotate that piece of calcite, the images of the calcite writing will actually move around a little bit. That's called birefringence. Here are the structures of calcite on the left and dolomite on the right. They're pretty similar in that there are, in calcite, a bunch of calcium ions and then a layer of carbonate ions. And as you spin this, you can see that that carbonate consists of a black carbon atom surrounded by those 3 red oxygens in a CO3 group, calcium carbonate. Dolomite's pretty similar, except some of those ions are replaced with green magnesium instead of the blue calcium. But it's still got those carbonate triangles, the CO3 ions, mixed in with calcium and magnesium. So no surprise, really, that, that they have similar properties because they have very similar structures. So those are the 10 non-silicate minerals that you'll need to be able to identify. Along with the 8 silicates, there are 18 minerals we want you to be able to identify based on the properties that we talked about in these 2 videos.